For our second example of a continuous charge distribution, we have an infinitely long charge distribution, straight line, so that's what these dashed lines at the top and the bottom mean, that it's infinitely long. And we want to find the electric field at some point P along the x-axis based on this whole long charge distribution. Well, one parameter that we need to define we'll call lambda. In this case, lambda does not represent wavelength. Lambda is a value that is basically the charge per length. So this charge per length is a quantity that defines for every specific length how much charge is in there contained in that length. Now let's start drawing some vectors here. And let's take some differential, we'll call this dy. We'll say this line is on the y-axis, so we'll call that dy. And there is a vector that comes down through this point. And you notice that I have an x component and a y component. And then I'm going to take the corresponding differential y, dy, and draw a vector. And again, I have an x component and a y component. Now, it turns out that because my charge is linearly distributed along this line, that the charge dq inside of dy is going to be the same. So again, my y components are going to cancel. And also my angle theta are going to be the same. And also, the other thing I know is that my differential length is some distance y from this origin. And I'm going to know x, that will be given to me. And the only other point that I really kind of need to know is this distance from the differential length to the point, that's r, and r then is the triangle, the right triangle, it's the hypotenuse, so this is going to be square root of x squared plus y squared. Okay, so we have our differential electric field, is equal to 1 over 4 pi epsilon naught dq over r squared. And remember, because we canceled out the y, then we have to multiply by cosine of theta. Now I need to find dq, Well, let's look at it to find dq this way. I know that my total charge is equal to lambda times L because of this equation. I'm just rearranging this charge per length. And L we're going to put in terms of y because that's the variable we're using here. And if I make a differential of charge, well, lambda is a constant. And so we can't make a differential out of it, but we can make a differential distance. So let's put in what we know. We'll have lambda dy over 4 pi epsilon naught r squared. Well, that's just the square root squared, so that's going to give me x squared plus y squared. And I have a cosine theta at the top. Okay, so now I have to figure out what are constants and what are not constants. Well, lambda is a constant, 4 pi epsilon naught is a constant. I have the dy, well, I have a y here in the denominator, and cosine theta is actually dependent upon y in a way. So I can't get rid of this. I can't consider this a constant. So I'm going to write my electric field is equal to, put my constants out front, and then I'm going to have an integral. Now, because this is infinite in length in both directions, I'm going to put from negative infinity to infinity dy, well, actually it's easier, it's nicer if I write it cosine theta dy over x squared plus y squared. Okay, now I have this cosine theta, and I really need to get rid of it. And in the process of getting rid of this cosine theta, I'm going to really want to deal with my differential y also. So let's start with y. So if I take y is equal to x times tangent of theta, and that's just the definition of tangent function based on this triangle. And I take and I do the derivative of y with respect to theta. That's just going to equal x, which is not part, it's just a constant at this point, divided by cosine squared theta. So differential y is just going to be x d theta over cosine squared theta. Now let's look at what we can do with cosine theta. Cosine theta is just equal to x over square root of x squared plus y squared. And if I square everything, then I get cosine squared theta is equal to x squared over x squared plus y squared. And if I want to put x squared plus y squared together on one side, so I'm going to have 1 over x squared plus y squared, that's just going to equal to cosine squared theta over x squared. Okay, there's a lot of stuff here, so let's start putting things together. So my electric field equal to lambda over 4 pi epsilon naught integral negative infinity to infinity, and I have a 1 over the let's see, 1 over this is this cosine squared theta, and I have dy to put in. So I'm going to have cosine theta, and I'll have a cosine squared theta over x and x squared, and I will have an x d theta over cosine squared theta. Well, I'm going to have the cosine squared thetas cancel. One of the x's is going to go away, and so that I get rid of one x in the bottom. And x is a constant, so I can bring that out, and my integral simplifies. So I'm going to have an x in the bottom, and now all I have in the integral and then remember this is for y. Y equals negative infinity to infinity. But now I've got cosine of theta d theta. So I have to reevaluate these limits based on angle. Well, here's a little theoretical mathematics to think about. If this line is infinite, then the only way that I can integrate at an infinite point is if this angle becomes parallel to this wire at both ends. Basically what we're saying is, and this is where things get kind of crazy, that to cross a line at infinity requires two parallel lines. Right? So if I want to cross at infinity, I've got to have a parallel line to be able to cross at infinity. And that just means that I need to integrate from one parallel side all the way through to the other parallel side. And so this angle is going to be from pi over 2 to, or I can go from negative pi over 2 to pi over 2. and that would be cosine theta d theta. Okay, so have our constants here at the front. Integral of cosine of theta is sine of theta, and we have limits of pi over 2 and negative pi over 2. So that's just going to be our constants, lambda over 4 pi epsilon naught times x. Sine of pi over 2 is 1 minus sine of negative pi over 2 is minus 1. And this is just going to be 2, which is going to cancel out, factor out with this 4. And that gives me lambda over 2 pi epsilon naught x. Now, remember, if I look at this wire from top, I'm looking straight down, and here is my point P. This rule is valid if I look in this direction, this direction, this direction. Everything that's on a circle no matter which angle I go will have this as my electric field strength. So this is an important formula to remember. We will come back to this one a number of times, so it's a good one to remember. There's some homework assignments that you'll need to remember this one, and it's a good one to know for just general. But this one, it took a little bit of extra work. Kind of had to use our brains on this one because we had to do some simplifications, and we based these simplifications on just strict trigonometry plus calculus. So sometimes we have to kind of look at all sorts of different relationships and see what we can do to simplify our problems. It makes it a little bit easier. So next we'll look at another charge distribution, and it's going to use something that we came up with in example 1.